Hi, welcome to this lesson on Analytical Geometry, Circles Part 3. Let's have a look at some properties of circles within Analytical Geometry. So just as we looked at properties of circles from a geometrical standpoint using circle theorems, we can now observe some algebraic structure on these circles using Analytical Geometry. So let's have a look at circles with the same center. So circles with the same center have each of their radius lines originating from a common center point. So this common center point here, C, the radius goes from here to the smallest circle. I can call that R1. And that same radius originates from that center going R2. Okay. And in this case, we can see the circle, the blue circle of radius R2 is much bigger because it has a larger radius, but they both have the same center. So we say that the distance between the two centers is d equals 0 because they both have the same center, so there's no two different center points. So there's no distance between the centers. Okay, circles that touch each other internally, so internally meaning inside, at one common point, have the following property. So again, here I have in blue a circle with a large radius, let's call it R1. And then I have a red circle which only touches the blue circle inside at one point. And that red circle has a radius of R2. Then we say that the distance between the two centers, the blue center and the red center, is the entire distance of the blue center minus the distance of the red center. So R1 minus R2, and that will be the distance between the two centers of the circle. Circles that intersect, so cut each other at 2 points, the distance between the two centers is less than the sum of the two radii. So let's see what we mean here. So here we have an instance where you have a circle in blue with a radius of R1 and a circle in red with a radius of R2. If they intersect each other at 2 points, then we can observe from their centers a radius length R1 here at that common point of intersection, and a radius length of R2 at that point of intersection. Then we are saying that the distance between those two centers is less than the distance of R1 plus R2. And again, this is the famous what we call triangle inequality, because you can see it from a triangle inequality. And it basically just says that the distance between the points, let's call them A and B, that's always going to be a shorter distance than if you went through another common point C. So if I went from A to C and then from C to B, adding those two distances together will always be larger than just traveling in a straight line. So what this triangle inequality is saying is that the distance, the shortest distance in the normal plane that we are used to, the Euclidean plane, is a straight line. Okay, so when 2 points intersect each other, what will happen is that the radius lines, when you sum them together, will be larger than the distance. Okay, and if you want to try and visualize why that is true, then think about it this way. So I'm going to highlight the radius lines here, R1. So imagine you've rotated it down, and now it makes up that much here. Then imagine you took the same radius lines, let's put it in blue, okay, R2 over here, and then you rotate it down, so you get that distance over here. Now look at that. You've traveled you've traveled more than d units, because what you've done is you've got this extra length here plus this length here in pink. So there's a sort of intersection there that gets added twice. That's going to be larger than that flat line d, okay, because you're adding more. So essentially you're going to have the pink line that looks like this. Okay, so if I superimpose it below here, there's the pink line over there. Okay, and then the blue line, if I add it on top of that, so from that same line now, it's going to look something like that. So this distance here is much larger than the green distance between the centers of the circle, okay, which is over there. Okay, so you get a larger distance. Then circles that touch externally, so outside at a common point, in this case that common point over here, call it A, then the distance between the two centers is equal to the sum of the two radii. So before, when the circles cut each other, the distance of the centers was less than the sum of the radii, But now the sum of the radii is exactly the same distance as the centers because they are only touching at one common point. And we can see this. The blue circle has radius 1 and the red circle has radius 2. And the center, the distance between the centers is that radius 1 plus that radius 2. Okay, so that's when it's exactly equal. And then circles that do not touch at any point. Okay, so you can see here, they are not touching and they are essentially outside from each other. Okay, that's important that they are outside because we looked at what happens when they were internal. When they were internal, it was given by this distance here. Okay, but now it's external and they are not touching each other. Then the distance between the two centers is going to be greater than the sum of the two radii. And again, we can see why. This, from this blue point here to that point there, that's radius 1. And then this is radius 2. And there's a little gap here. And that little gap added together makes the entire distance of the center. So we can see that the distance of the center is greater than the sum of the two radii. Okay, so why is this important? Well, if we are describing circles, mainly through their key characteristic of their center and their radius length, then we can tell when two circles, for example, are intersecting each other at 2 points, when they are only touching at 1 point, when they are external from both of each other and not touching, in this case here, or when they are just touching internally at 1 point. We can tell when that happens algebraically by observing distance from centers and the radius sums of each of these circles by these formula here. Okay, so those are properties of circles within analytical geometry. We will utilize those properties to answer further questions. All right, I'll see you in the next one.